How's it going? How's it going, Nora?
Hey, Professor. It's going all right. How are you?
Not too bad.
Yeah,
Trying to play catch up and avoid the bad weather and all that good stuff.
sounds good. It's been busy lately. It's been crazy. Life has just been like, I feel like it's like got three fists punching me at all times.
Well,
But,
that's a good scenario.
all right. I had a question.
Go
Hopefully
for
it's okay before class, but so the 20 chapter 22 isn't on the midterm, but we're gonna be doing 22 this week for homework.
it. No, I'm in the process of changing that right now
Oh,
as you're talking to me. I'm actually just changing all the dates. I'm putting them all on 7:30 just to try to keep from having the repeated problem where people are freaking out. So just
I
put them
know that
all due on 7:30 and move them earlier.
yeah, it's been a mess because
Yeah,
it's like
it's
it's
not.
so hard to change the dates and stuff, but it's like
Yeah, it's a pain in the butt. So I feel you. So I think I just got those. Let's see if it actually takes. Sometimes it barks at me. Yes, it took everything. So 22, we will begin covering next meeting. And I think that's all we'll really need, to be honest with you, because the way it works is 22 is Gauss's law, and then we end up using Gauss's law for the next two chapters in a row. So you don't have to spend much time on actual Gauss's law because it's going to be covered so much
gotcha.
in the subsequent chapters.
Okay, did
But
we need
I'll probably still make it at least Wednesday of next week before chapter 22 is due.
Oh, gotcha. Okay.
What do
I
I
was
got
just
right
gonna check
now?
real quick and make sure that it's sent to us too, because some I don't know if there's like a miscommunication or anything when you change dates, but basically everything up to chapter 25 is past due. And I was
Yeah,
like,
yeah.
oh.
Yeah, I just noticed that. I'm like, oh man. So yeah, chapter 22. I didn't move that one, so I'm going to move it now. Oh, that's the day. I gotcha. So I'm going to make it. You guys meet on Wednesday, so I'll make it Tuesday. 7/4. That should give us enough time. If I find out it's not, then I'll reevaluate. But I'm giving it till 11:59 p.m. on. So you know what? That's friggin' the day before. Or that's actually July 4th. I'm going to make it the 7th. Just that's a very abnormal date for me to do, but
Hmm, it's fine.
nah, I'll do it ninth. What the heck? But it's
And we
probably going to have
also
23 due then. Go
we
ahead.
also had a professor. We also had like chapter 20, 26, 27 due by this week, and everything between 22 to 25 already passed due. Just so you know.
No, no, no. We only have 21 due this week now. He just changed that. And then next week we're gonna have 22 due.
Yeah,
And
Boha,
I,
then
I'm
you
I'm
were
I'm
right
saying
up until 2 minutes ago.
Yeah, I'm saying on the Kevin's app,
Oh,
actually,
gotcha.
yeah, actually it's saying that we also like even chapter 26, 27, we had to do this weekend.
Yeah, never pay attention to the Canvas due date as far as what it says like under the assignment.
Mhm.
But yeah, I just finished changing them in my lab and mastering, so we at least got that address.
Thank you.
You're welcome.
And also so I still had a problem with my test one, the one like in-person test.
Right.
The grade is still not changing, just you know.
Okay. Thanks for letting me know that. I will check that out. I don't know why that's so. That's kind of weird. Anyways, it's actually time to begin class. So does anybody have any other questions before we get cracking? I gotta check out Bohan's test. If you don't see it change, Bohan, let me know.
Yeah.
Definitely before the end of the semester or at the end of the semester, just in case I forget, but it should be taken care of soon.
I can't see your screen now. I don't know what's going on. It's just my computer issue.
Can everybody else see me?
Yeah, you're good.
Okay.
Okay, I'm
Yeah,
just
send one out on you,
I'll
Bohan.
just restart my computer real quick. I can't see the screen now.
Professor,
Yes,
is
sir.
that
Yes, ma'am.
that
Sorry.
next test going to be tomorrow? Because there was like chapters
I'm-
21 and 22 practice tests, or is
Yeah,
that
I moved that too. That
okay?
was something I noticed. One, it was supposed to be chapter 21 and 22, but y'all haven't covered 22 yet. So what I ended up doing was I moved it, I think, until the 9th. Let me double check.
Oh, okay. I was just
Yeah.
wondering if you're moving
Yeah,
it, then
practice test
that's
3 is
fine.
now
Yeah.
July 9th, and that's also when the test 3 should be available, not the midterm, but test 3. I
Yeah.
have still up there is practice midterm for chapter 17 to 22. I'm in the process of making one that's 17 to 21. So just keep an eye out for that. It's okay to continue doing that one. It's just one or two questions every time you take it will be from chapter 22, and we're not covering that, so it's not very helpful to you.
Mm-hmm.
Anybody else have anything?
All right. Thank you, Professor.
Professor, I have a question. It's on our textbook.
Uh-huh.
It just all of the formula that I don't understand. Looks weird to me. It's on chapter 21. If you look at I think
Okay.
it's on the last page of that chapter. It's like a summary of all the equation. So that is I forgot what page it is, but it's a chapter 21, the equation 21, tag 4.
Okay, I'm pulling it up now. Let's see. Chapter 21. It takes a couple seconds for it to open the book,
Okay,
but
sure.
that's what I'm doing. So, and you say it's like in the recap of chapter 21, like at the end or whatever.
Yeah.
Okay, I'll check that. So summary.
Summary. Try to try to see if I can.
Oh, 21-2, 21-2, 21-1, 21-2.
No, yeah, I was asking like 21 tag 4. So the E, I can't see the first part, but the second part, why they had the 2Q, Q1, Q2?
Yeah, that's a typo. Yeah, it should just be Q over R squared. Yep, they made a boo-boo on that one.
Okay. Because if you don't have a 2Q, it's exactly same with the F, right?
Right.
That should be just 1Q, not Q1, Q2.
Yep.
Okay.
I'm typing it in there so we'll know for future. It should only have Q in the new. All right, and I clicked share note, I highlighted it and all that good stuff. So that should be taken care of. Thank you for checking that. And that's it's so funny. It's a brand new edition. They already got errors. So
Thank you.
you're welcome. All right. So when we last talked, I had worked a pretty hairy integral problem. So I want to I want to continue that because I know how much you loved it. So so actually I gotta do a couple more, and we're just going to use the same process that I went through. But that's sort of the key, is you got to sort of understand the process, and what you're doing is a very challenging problem, but it's a challenging problem that has a very specific sequence of steps to follow. So let's get started on that. What I'm going to do is I'm going to draw a coordinate system. Actually, I'm going to undo that because that was ugly. And now I'm going to draw a coordinate system again. Okay, and I'm going to draw a coordinate system again. And we'll draw a coordinate system again. Like so.
Professor, I don't think you're sharing with us yet.
I am not. That's I was just in the process of changing that over, but thanks.
Oh, okay, gotcha.
I literally just started doing it as soon as I heard the beep. But it looks really good. I'll just tell you that's what y'all need to know, is how good it looks. You don't have to actually see it. You just need to know how good it looks. All right. So now let's pull this up. Screen mirroring. This should be it, hopefully. Okay, so last time what I did was I had a infinitely long line of charge that was uniformly distributed along the line, and we represented that by saying that lambda, the charge density or the charge per unit length, was a constant. This time I'm going to have a similar scenario, only instead of having a straight line charge, I'm actually going to have a loop of charge. Like that. And technically it should be centered like that. So that's a little better. So there's your loop of charge. I'm going to make a lot of use this semester of the coordinate systems known as like spherical coordinates, cylindrical coordinates, and all that good stuff. So I'll do a little bit of that. There's X, there's Y, and then this, of course, is Z. And there exists a coordinate system that's just like polar, which hopefully everybody's had. Has anybody not seen polar coordinates before, where you have an R and a theta? We usually do that in trig. Well, if you add to polar coordinates, where basically you normally have a point X comma Y in a pair of parentheses that are called ordered pairs. Well, that can also be represented, instead of X comma Y, you can represent it as parenthesis R comma theta. And theta is measured from the positive x-axis. If you're looking down at it from the z-axis, it's measured counterclockwise towards the positive y-axis. And R is just the distance from the origin to the point. So R is actually square root of x squared plus y squared. And then theta is the, you can call it the inverse tangent of y over x, for instance. That's how the polar coordinates work. But if you wanted cylindrical coordinates, the only difference is you'd add a z-axis. So you'd have, instead of parenthesis x comma y comma z, close parenthesis, we'd have parenthesis r comma theta comma z, close parenthesis. So that's one of the systems we use, and that's actually a good system to use here. So what I'm going to do is I'm going to say charge is uniformly distributed along a circular loop of wire of radius big R. The total charge of the loop is big Q, and we want to know the electric field a distance Z above the loop's center. Okay, so that's our scenario here. So what I'm saying is right up here, there's a point along the Z-axis that's a distance Z from the origin, and that's the location where we'd like to know the electric field strength. Now, what we do know, and I'll do this here, so let's say solution. What we do know is that the differential electric field can be written, and in this case, I'm going to say as dq over 4 pi epsilon naught. And then I'm going to say RP dq cubed times RP dq. Like that. Where RP dq is defined to be RP minus R dq. Okay, so the process here that we repeat over and over again is we're going to use this little expression, this dE equals all that junk, and we've got to figure out what dq is. And the rule with dq is that dq is equal to lambda dl, or it's equal to sigma dA, or is equal to rho dV. We also have to find RP, which is the vector that points from the origin of your coordinate system to the point at which you wish to know the magnetic field. So we can, or excuse me, the electric field. So right here, we can also call this point P. And we need to know RDQ, which is a vector that points from your coordinate origin to the little differential charge element that you've chosen. Normally, that should be chosen to be like in the first quadrant, or at least in the quadrant where X, Y, and Z are all positive or zero. So it can be on the actual axis. So that's the scenario here. We're going on the assumption that we actually know R and Q. Even though we're using them as symbols, we're pretending we know those. So what I'm going to do is I'm going to first imagine an arbitrary section of charge, and that arbitrary section of charge is going to be right here. Okay. And the way that's going to work for me is I am going to say that this right here is out an angle theta. And if you go over to this spot, then this is an angle theta plus d theta. In other words, if you go all the way from the x-axis to the other side of that pizza slice, then that total angle is theta plus d theta, or the angle across the itty-bitty pizza slice is just d theta. Okay. We also know, for instance, that the radius is r, so that tells us a little something. But this little segment right here is dq, and we're going to call dq, we're going to call it r times d theta times, actually, let me redo that and write it in a little better place. So dq is going to be lambda times r d theta, like that. So what we're seeing is, as I said before, dq can be lambda dl. In this case, the dl is like from trigonometry when you learned about radians. S equals r times theta gives you the arc length s, represented by a piece of a circle whose width is theta radians and whose radius is r. So r d theta is the length dl, and lambda is the charge per unit length. But because we know r and q, we can also say where lambda is equal to q over 2 pi big R. Okay, that's what I mean by it being uniform. So if you take a 1 millimeter length of the wire and you cut it off and measure the charge on it, then you take that charge and divide it by the length, you'll get some number. Well, that number will be the exact same as dividing q by 2 pi r, as long as you convert the units and everything. Okay. Now, can anybody looking at this describe the vector RP for me? Where would be the tail of the vector RP and where would be the head of the vector RP? Anybody? Remember, the RP points from the origin that you've chosen to the point at which you wish to know the electric field.
It could be like any of the sides of that triangle, right?
Not for this one. The P, this is the DQ. That little triangle that I just drew it points to the DQ. I did label P. You might not have noticed when I did it, but does everybody see where P is now?
Oh yeah, up there. So it's from the origin to Z?
Exactly. So can you guess how long it is?
Length Z.
Length Z.
Oh.
What would you multiply Z by to make it into a vector? So you need a vector. Which direction should it point first? Should it point a little bit in the y direction, a little bit in the x direction, a little bit in the
Is
direction?
it J hat?
There you go, K hat.
K hat. Whoops.
Oh, I thought that's what you said. Yeah, notice it points from the origin to the point P. So I'll draw it up here and say that's RP. Now we can get back to what Nora was talking about, and I'm going to draw this one in black just so it'll stand out. This vector you can sort of think of as R dq. That one's a little more complicated because it clearly is lying in the XY plane and has an X component and a Y component. So I will work this one out for you, but I think you'll agree with my answer. So R dq is going to be basically R times cosine theta I hat plus R times sine theta j hat. Would y'all agree with that? So hopefully y'all can see, for instance, that, let's see if I can change this color. You can see that hopefully that's a Y component, and this green one right here is the X component. Actually, I probably shouldn't write it that way. So anyways, I just drew those green ones in there so you get a sense of what it is. And then you can see, oh yeah, that's another right triangle, because clearly the one parallel to the Z-axis is perpendicular to the one parallel to the Y-axis. So that's why it came out the way it did. Does that make sense to everyone? And I should probably redraw my little vector symbol for the R dq vector. So now I've actually determined what dq is. I've determined what rp is. I've determined what rdq is. So now all I have to do is determine what rpdq is. And rp, rpdq is supposed to be rp minus rdq. And we'll, of course, need that magnitude too, because that goes in the denominator. So I think you will all agree that this is z k hat minus r cosine theta I hat minus r sine theta j hat. I'm also going to, let's use this ugly color right here. This vector right here, that turns out to be RP DQ. And I just want to show you that so you'd have some understanding of where it is. Can somebody now use that image of RPDQ to tell me how long RPDQ is? In other words, tell me a formula for calculating this length.
Should be the two sides squared equals RDP squared.
Exactly.
Yeah.
And one side is Z and the other side is big R.
Yeah, I did.
So good job. So that's all the quote unquote hard stuff. Once you filled this in and put your limits of integration, you've done all the physics. So here's the magnitude of RPDQ. It's actually equal to the square root of Z squared plus R squared. Now, if you, just to refresh your memory, by the way, the Pythagorean theorem works in 3 dimensions too. So you could have said Z squared plus parentheses negative R cosine theta close parentheses squared plus parentheses negative R sine theta close parentheses squared, and taking the square root of all that, and that would be exactly the same thing. But because the last two terms has a common R squared in it, you can factor that out, and that would leave you R squared times parentheses sine squared plus cosine squared. And everybody knows that sine squared plus cosine squared is
1.
1. There you go. So that's why that ultimately reduces to that simple form. Okay. All right. Now that we got that, I can say E is equal to the integral of dE, which equals, I'm going to go ahead and pull out the lambda and the R and the 4 pi epsilon naught. So I'm going to say lambda R over 4 pi epsilon naught. Those are all things that were in the formula for dE. I'm pulling them out in front of the integral. What I have left is, notice dq was lambda times r times d theta. I've already got rid of the lambda and the r, so all I got left here is the d theta. And then I have in the bottom, I have z squared plus r squared to the 3/2 power, because 1/2 power is the square root and it was cubed. And then finally, I also have the RP minus RDQ, which would be parentheses Z K hat minus R cosine theta I hat minus R sine theta J hat. Okay. So at this point, you've essentially done almost all the physics. There's a little bit of physics left. And in fact, your book uses this part specifically to make the problem a little easier. I'm going to change where I put this just because I don't like how ugly it looks off center. So yeah, that's me. That's the kind of guy I am. All right. So I did that. Now this is going to be Z squared plus R squared to the 3 halves. So we're going to integrate this from theta equals 0 to 2 pi radians because it needs to go around the entire circle. Does that make sense? Now, what I wanted you to realize is if the DQ is right where we have it drawn, then the DE is right here. Right? And I think you see, if you looked at a DQ back here, that would actually have exactly the opposite X and Y components, but would in fact have the same Z component. Do y'all agree with that? And because it has the opposite Y and X and Y components, that means that the X and Y components would cancel out. So that's physically what's going on when you're out here, say at 45 degrees, there's another one at 180 plus 45 degrees that does exactly the same thing, at least in terms of the X component and the Y component. The Z components add though. So what you should be able to tell from this is that clearly the I and the J should ultimately integrate to 0. And that's by symmetry. Okay. Does everybody understand how that played out?
You mind repeating that, please?
Yes. So if you look at the DQ that I have drawn, the little black speck on the wire, and you go 180 degrees from that, you'll see there's an identical DQ that would be in the negative X, negative Y quadrant. And that would in fact have the exact same Z component as the electric field does for the original DQ, but it'll have the negative of the X component and the negative of the Y component. Therefore, that particular DQ will be canceled by its mirror at 180 degrees. At least the X and Y components will be, but the Z will actually add to it. Because you can say that for any DQ, that means the symmetry of the problem forces the I hat and J hat components of the electric field to integrate to 0. So you expect this answer to only have a Z component.
Okay, thank you. That makes a lot more sense.
No problem. Now you'll also notice that we're only integrating with respect to theta, right? So if you didn't catch that physically, you might know it mathematically, because if you integrate cosine theta from 0 to 2 pi, the symmetry of it is that the first pi over 2 is positive, and then the next from pi over 2 to 3 pi over 2 is all negative, and it's twice as big as the 0 to pi over 2. And then you have another positive that's half as big as that. So these add up to give you 0. The same thing's true for the sine. If you integrate from 0 to pi, you get one value. And then when you integrate from pi to 2 pi, you get the exact same but negative. So those would integrate to 0 as well. So you can tell by it mathematically, or you can tell by it physically. Okay. Yeah, I think that's it. Okay, so we now have this, and now our job is to figure out basically what's going on. So we know the z isn't going to change. We know the r isn't going to change. And in fact, I can pull that out in front. And ultimately, all I'm going to get is lambda. Oops, I should probably write back the same color I was writing. So I'm going to get lambda r over 4 pi epsilon naught z squared plus r squared to the 3/2, like so. And then I'm going to get a k hat in front and a z in front, and I'm going to get the integral of d theta from 0 to 2 pi. So obviously this integral is really super easy. Your integral of d theta is just theta, and then you evaluate it from 2 pi, which gives you 2 pi, to 0, which gives you 0. So ultimately, I'm going to say 2 pi times r times lambda times z. All of that was in the numerator. And now in the bottom is 4 pi epsilon naught z squared plus r squared to the 3/2, and all of this points in the k hat direction. The reason why I write it that way, namely pulling the r out in front and not canceling out the 2 pi, is because you can see now 2 pi r times lambda, what's that going to be?
Q.
Exactly. So ultimately, I can now say that the electric field for this is in fact equal to QZ over 4 pi epsilon naught z squared plus r squared to the 3/2 k hat. Any questions on that? So that's pretty straightforward, right? So notice the steps. The steps are, okay, Mr. Younger's given us this formula, dE is equal to dQ times RP minus RdQ, or actually you should just call it RP dQ, divided by 4 pi epsilon naught times the magnitude of RP dQ. And my job is just to go ahead and actually figure out what each of those little parts are. Now, this is not drawn very well, so I'm going to try to clean it up a little bit. But that's my place here, is to try to make this work by knowing what the definitions of all these terms are. So now I can do all that. I can do this right here. Whoa, might want that to be in red, huh? So this is P dQ, and that's the third power there. Okay, so I've got these little parts. I've got the dQ. I've got to figure out that what that is. That's going to either be lambda dL, sigma dA, where dA is a differential area, or rho dV, where dV is a differential volume. So we know what formula to use. We just have to figure out from the symmetry which one of the three we're going to use. Then we got to figure out the vector RP, which points from the origin to where we want to know the electric field. And then we got to figure out the vector RdQ, which points from the origin to a particularly instructive differential charge element. If I would have chose it right on the x-axis, that would not be particularly instructive, because I would have found it to just be x I hat, right? So I try to choose in the middle of a positive quadrant, or octant in the case of 3 dimensions. And then that gives me the generality that I need. Once I have RP, RDQ, and DQ, then I can do RP minus RDQ to figure out one vector, the RP DQ vector, and then I can take the magnitude of it either by looking at the figure or remembering that the Pythagorean theorem works in 3 dimensions. So this is the actual formula, and it's actually kind of helpful because it turns out the next problem we're going to solve is very similar. Specifically, we're going to try to find the electric field over a plate like that. So instead of a loop of charge, we're going to have a plate that's uniformly charged, whose radiuses are, and it's circular and all that good stuff. So does anybody have any questions on this before we move on to that next one? All right. So I will be referring back and forth to that, but let me first off draw some coordinates again. Okay, that's it. Now I'm going to draw another ellipse because I'm supposed to be representing an ellipse in 3 space, sort of. So that's going to be a circular disc, if you will, but because we're looking at it in 2 dimensions, when it's a 3-dimensional doohickey, we have to draw it elliptical so it can show some shape. If you wanted to, for instance, you could draw lines on there to show that it's solid. The main thing is we have a uniformly charged circular disc of radius R and total charge Q is in an X, Y, Z coordinate system as shown. What is the E field? A distance Z above its center. I'll say note, sigma is equal to Q over pi R squared. Okay, so sigma is the charge per unit area, and by writing it that way, I can leave the expression in terms of Q, or I can leave the expression in terms of sigma. It's actually going to be helpful to have it in both ways, sort of. I am going to call these axes like I did before. This is the x-axis. This is the y-axis. This is the z-axis. I have a distance z up here is the point P. So that's where I want to know the electric field. And what I'm going to do now is, oddly enough, I'm not going to do the typical thing that I did with the last 2 problems because y'all are getting just way too comfortable with that. So I got to make it more complicated. No, it turns out to do it that way, you'd actually have to use a double integral. And that's beyond the scope of what's required of this course. It's often not covered until well into the second semester of calculus, if not the third semester. So we're not going to do that. I will tell you that if you knew the double and triple integrals, it'd be a lot easier to do it that way. But what we're going to do is we're going to use this. What we know for a ring of charge uniformly distributed, we know that dE is equal to Z dq over 4 pi epsilon naught Z squared plus R squared to the 3/2 K hat. So this is supposed to have some resemblance to the last expression we found, which was QZ over 4 pi epsilon naught Z squared plus R squared to the 3/2 times K. So that's what we're doing. Does everybody understand how I went from that answer down there at the bottom to this? All right, now I'm going to attempt to draw another ellipse, hopefully a good one. And then another one. Like so. So that's supposed to be the little differential charge element, if you will. Now, you know how to actually find out the area in that. You would take pi r plus dr squared and subtract from it pi r squared, where you're saying r is the inner radius to that little red ring. Does that make sense to everyone? But it turns out if you really went through that process, you would get some terms that would be of the order of dr squared and stuff like that. And when you're taking the limit as dr approaches infinitesimally small, a dr squared is really, really small compared to a dr. So it turns out that this dq right here can be represented by sigma times 2 pi r dr. So it's like imagining that you took and cut that, say, along the y-axis, and you laid it out flat and it made a rectangle. You know, for real, it's not going to make a rectangle because that inner radius would be one top of the rectangle, and that outer radius or that outer circumference is going to be the bottom of that rectangle. And obviously the outer circumference is bigger than the inner circumference. So you would actually get basically a rectangle with little triangles at each end. But it turns out that those little triangles differ from the, those little triangles cause the change in dA to differ by an amount that's proportional to dr squared. So that's why we can ignore it. So what we're really doing is we're pretending like this thing is a rectangle whose circumference is 2 pi r and whose thickness or height is just dr. So that's why I've used that. Okay. I actually did cover this quite a bit on my YouTube channel. You can see me going through the process of showing you that you really don't need to include other terms, because in the limit as dr approaches infinitesimally small, i.e. 0, then those other terms are irrelevant. So dq, as I said, is going to be sigma times 2 pi r dr. Not only that, because I'm now allowing r to vary, I can't write this r as r anymore. I've got to write it as little r. So I'm going to go back and change this to little r. Does everybody see why I had to change that to little r now? So that right there, the radius from the origin to the outside edge of the disk is big R, but we're taking a little segment, a little ribbon, if you will, or circular ribbon of charge and treating that as the d cubed. So now I can say E is equal to the integral of dE, which equals, let's write Z, let's write sigma, and let's write 2 pi over 4 pi epsilon naught integral of RdR over Z squared plus R squared to the 3/2. And let's put this little k hat out in front. Okay. So this one might look a little bit difficult, but it's really not, because we've got that R on top, but we're going to integrate this from R equals 0 to big R. We can make some cancellations. For instance, you can already see that the 2 pi and the 4 pi do cancel out, which they did before as well, but we had reasons for not doing it. I'm going to go ahead and do that cancellation. So I'm going to say sigma Z over 2 epsilon naught is what I have left out in front, plus the k hat. And then I'm going to say let U equal Z squared plus R squared implies DU is equal to 2R dr. Oops, ran out of space there. Let's do this. So now I can say implies du is equal to 2R dr. Okay, so I don't currently have a 2 out in front, but I have a RDR, so I can multiply by 2 and divide by 2 simultaneously, and that'll give me a 2 in the bottom here. So let's mark this out and make it a 4. And now I'm going to say the integral of du over u to the 3/2. Okay, of course, that's the same thing as the integral of u to the negative 3/2. And the integral of u to the negative 3/2 is u to the negative 1/2 divided by negative 1/2, which is the same thing as multiplying by negative 2. So that'll get that, get rid of that 2 that we just added, and I'll have sigma Z over 2 epsilon naught. I got a negative here now though, and I got a k hat, and then I've now got Z squared plus R squared from R equals 0 to big R, and that's to the negative 1/2 power. So actually, let me make this space a little bigger. So Z squared, wow, man, darn it. Z squared plus R squared to the negative 1/2. And now I'm going to evaluate that from R equals 0 to big R. So when I do that, I'm going to get negative sigma Z over 2 epsilon naught, k hat. And then, of course, the first one's going to be 1 over the square root of R squared plus, let's do R squared plus Z squared. And then when R equals 0, this will be minus 1 over the square root of Z squared. So that's basically 1 over the square root of Z. Okay. Now, if we put this in the opposite order, in other words, we put the 1 over Z term first, then we could get rid of that negative. And in fact, it would still be, it would actually be a positive quantity. So that's good. We're going to do that. We're going to say equals sigma z over 2 epsilon naught k hat. And I'm going to go a little further and I'm going to factor out a common factor of z in the bottom. Okay. So if I do that, I'll have 1 over z times, now it'll just be 1 minus. In order for me to pull that out, I have to pretend there was a z under the r, if you will, or excuse me, in place of the r, if you will. So this is going to become 1 over the square root of r squared. Let's do it like this: r over z squared plus 1. Notice if I pulled that z back in there, in the square root, it would become z squared, and it would come inside. I'm trying to do this, not good. Let's do this. It would come inside and cancel out the z in the bottom. That's how I know the z on the bottom is the right thing to have. So I'm going to say z there plus, in this case, it was just 1, and it was just that. So that's what I have. You can also see that now we can say E is equal to, notice the z's cancel out. That'll be sigma over 2 epsilon naught times 1 minus 1 over the square root of r over z plus 1 quantity squared there. And all that times k hat. That's actually the complete answer. Anybody have any questions on that? Now, the cool thing about this is if you consider where z is much smaller than r, if z is much smaller than r, then basically what you end up getting is that r is like going to infinity, and you end up getting basically 1 minus 1 over the square root of infinity, right? So basically the 1 over the square root term completely disappears, and you just get sigma over 2 epsilon naught, which is actually exactly what we'll find is the electric field strength above a conductor that's uniformly charged with a charge per unit area sigma. So that's kind of helpful. You can also consider, in the case of z being much greater than r, it should ultimately reduce to something like a point charge, and it does that as well. So anybody have any questions on that one?
I have one question.
Yes.
How did you replace the ZR with the sigma in like one of the middle steps?
Okay, so what I had before, let's see, I'm trying to look where a ZR was.
Like
Are
the
you talking about
ZR 2 pi.
So are you okay? That's what you're using. Gotcha. Okay, yeah. So the E equals the integral of dE equals Z sigma times 2 pi times k hat times the integral. Is that the part you were talking about roughly?
Yeah.
Okay, so what happened there was dq, as I wrote up at the top, was equal to sigma times 2 pi r dr. So that 2 pi just came from the 2 pi r dr. The sigma was up there. And then I just used that 2 pi to cancel out with the 4 pi downstairs and left just 2 in the bottom.
Oh, okay. I didn't see that note up top. That makes more sense.
I got you. Okay. So everybody follow that? All right, so that's another iteration of using integrals. What I would recommend, as I mentioned to you before, that infinite line of charge that we did, you should try to do that, allowing it not to be infinite. So, for instance, instead of it going from negative infinity to positive infinity or along the y-axis, consider it maybe starting at negative L over 2 and going up to positive L over 2. That's a good intermediate step, because you got to do all the same things we did before, but this time you're going to do it and you're just going to shorten the integral by actually doing it over a specific range. You're still going to get that the y components are 0, or the component that's parallel to the y is going to be 0. So that's kind of nice. You can still get that. And you can do the integral, you can do the same, trig substitution, all that good stuff. Another thing you can do is you can let the bottom of the wire go not to L over 2 and the top of the wire to go to positive L over 2, but make it asymmetric. So, or even unsymmetric, just allow it to go from, say, negative L to 4L or something like that. So that's another way you can do it. And in that case, you're not going to have those cancellations by symmetry, because there's more above the center than there is below the center. It's going to go from negative L to 4L. So the whole length is 5L, and 4 of those L's are in the above the horizontal axis. So that's another thing you can do, and that'll give you a little practice. What I want to do now is I'm going to give you guys a 10-minute break, and then I'm going to show you some coordinate systems, just because we're going to use the symbols of them, not so much the actual coordinate system, but I am going to use the symbols of them, and it helps for you to have a picture. So let's go ahead and take a break, come back at 6:38. I'm going to stay here the whole time in case anybody has any questions, but go ahead and take a break till 6:38, and I'll wait for you. If you're still here, does anybody got any questions on anything?
Nope, all good.
That's cool.
What was the purpose of the absolute value on the Z again?
The reason why it had to be absolute value is because we were taking the square root of z squared, and the square root is the principal square root, so it has to come out to be the positive value of z.
Oh, okay, gotcha.
Yeah, it's a weird little technicality, but that's the actual reason behind it. If I can stop yawning, that would be great. I'm gonna check out the news on Russia, see if any other exciting stuff has happened. It's kind of crazy what happened this weekend. Nothing new. They are having some sort of a quote unquote press conference with Putin and Krasnov and Shoigu. I don't know how to pronounce Shoigu's name. And Bortnikov. I'm sure Prigozhin's going to fall out of a window in the near future. All of a sudden, get a real bad stomach ache and die. Terrible. So that's about all that's happening. Ooh, asteroid that NASA redirected will pass Earth this weekend. That's kind of cool. About the excitement of all the news I found. Got about 5 more minutes. Call you guys back. Yeah. We got about 2 more minutes. I'm going through all my classes, my lab and mastering right now, trying to straighten up some weird due dates. About one more minute. All right, it's about time to start up. So let's go ahead and get started. I'm gonna finish off these three little dots here. And hopefully that'll all save. It did. Okay, so now I've got all that up to date. Oops. Where's my Zoom? Where's my Zoom? Oh, there it is. Okay. All right, so we've now shown you the last example of doing these integrals. In fact, the next chapter, we're going to find a way where if there's certain symmetries, we can apply Gauss's law, which, by the way, is Gauss's law. It's not Gauss's helpful hint that sometimes works. So it is always Gauss's law. It's just the way we tend to use it a lot in this course is in such a way that we're solving for an integrand. So it's an integral equation. It's got an integrand that's the electric field. And if there's certain symmetries present, we can extract that electric field's magnitude by making a hypothesis of the direction and the variables that the electric field depends on, and then get that. So it's kind of a nice follow-up to this. But in both cases, the stuff that I'm using here, as well as the stuff that I use in Gauss's law, it comes in really handy to know some other coordinate systems. So I wanted to introduce you a little bit to those. So let me start off by drawing a coordinate system. Again, in this case, I'm going to say okay, so this is going to be my x-axis. This is going to be my y-axis, and this is going to be my z-axis. And what I'm talking about here is cylindrical coordinates. Again, this is beyond really the scope of what the class is supposed to be, but it just makes a lot of things so much easier if I just at least introduce you to the symbols. What we're going to have is the variables r, theta, and z. Okay, so if you were, for instance, to take the normal scenario, you'd say, okay, well, this is out a distance x. And then you say, all right, well, this is out a distance y. And then you go up here and say, this is up a distance z. And this little point would be x, comma, y, comma, z. That's your Cartesian coordinates. Now, if instead you decided to say this distance from here to here is r, and this angle right here is theta, then you would say that this coordinate is in fact r, theta, and z. And that would be exactly right. Okay, so that's the cylindrical coordinate systems we're talking about. And in fact, there is even some unit vectors, just like we have over here. We have I hat j hat, and k hat. Well, out here, we're going to have, in fact, a vector that's parallel to r, that's r hat, a vector that goes in the direction of increasing theta and is called theta hat, and that only has I and j components. In other words, it has no z component. And then there is the k hat vector right here. So you've got all new unit vectors that we can make use of. The r hat, which only has x and y components, the theta hat, which only has x and y components, and then the k hat, which is the same old usual. So in fact, if you wanted to take the time, you could see, you could show very easily that r hat is in fact equal to cosine theta I hat plus sine theta j hat. And then you could also show that theta hat is in fact negative sine theta I hat plus cosine theta j hat, which lo and behold turns out to be d r hat over d theta. So that's kind of interesting. And of course, k hat is just k hat. The way you go about doing that, by the way, is you just draw your coordinate system with the r laying down on it. So for instance, we can look at, let's say the x-axis is right here. And let's say the y-axis is right here. And let's say I'm looking down at the x and y axis just at these points. And what you'd see is if I come out here, I would see an r vector that points that way. And I'd see this is my r hat, and I'd see a theta hat that points this way. And I could tell that this angle right here is theta. And obviously, if you take the cosine of theta and multiply it by the hypotenuse of this triangle actually has a magnitude of 1. So 1 times cosine theta is your x component. And then 1 times sine theta is your y component. So that's how I got the r hat. Over here, you can realize that this too is going to be theta, and it also has a hypotenuse equal to 1, but this guy is going to be negative 1 times the sine of theta, because it points in the negative x direction, and this one's going to be positive 1 times the cosine of theta. So that's how you get all that. It's very straightforward. And in fact, knowing this and knowing how to get these, you can get a lot of the formulas that you would cover in your dynamics class when they talk about, for instance, Coriolis force and all that stuff. So there's your cylindrical coordinates. Now let's try the spherical coordinates. That's a little more complicated, but it is actually really nice to at least have as a picture of a tool that you can make use of from time to time. Okay, so this is again going to be your x-axis. This is going to be your y-axis, and this is going to be your z-axis. And as always, you could have, for instance, come over here to x, then go out a distance like this, and then come over here to y and go out, and then come up here, say, and using a line parallel to that, you'd see that is in fact z. So this point right here again would be x, y, z, but in spherical coordinates, it becomes r theta phi. So how's that work? Well, it turns out that the distance from here to here is r. Notice this one, unlike the cylindrical coordinate, has a x, y, and z component. And in fact, r is equal to square root of x squared plus y squared plus z squared. Okay. The theta still turns out to be the same thing. That's going to be this angle right here. But the phi is what we call a polar angle. Okay. So phi is the polar angle. And theta is called the azimuthal angle. And in fact, you could call this little quantity, let's change colors for a second. You could call this little quantity right here, you can call that rho if you want. And you can see that rho is in fact equal to r times the sine of phi. Z is in fact equal to r times the cosine of phi. So that's one of the coordinate changing equations that's necessary, just like that one is. But when you get that, then you could say, okay, well, that means that theta, oops, darn it, keeps doing that crap. That means, for instance, that if you wanted to know x is equal to rho cosine theta, which is, of course, r cosine theta sine phi, and y is equal to rho sine theta, which of course is r sine theta, sine phi. So these are your transformation equations if you really wanted them. But you can also see how that's going to give you, in fact, that r hat is equal to cosine theta sine phi I hat plus sine theta sine phi j hat plus cosine phi k hat. So that's how you can get that. And of course, you could go ahead and figure out that theta hat is going to be essentially the same as theta hat was in the cylindrical coordinates. So you don't really have to deal with that, but that's how you change the r in there. The big thing here is, though, if you want to specify, for instance, a point or a function or a vector in cylindrical coordinates, then notice the r in cylindrical coordinates has a theta in it already. So really all you have to specify is the r vector along with the z component. And if you're doing that in spherical coordinates, you only have to do the r vector. So you can say, hey, this has a r coordinate of 3 meters or whatever times r hat. But because r hat has theta and phi in it, you see that it changes. So the main thing to know about this is whenever you're integrating or differentiating, unless you have I, j, and k, or x hat, y hat, and k hat, or excuse me, x hat, y hat, and z hat, then you actually have to deal with the derivatives and the integrals of those unit vectors. But anyways, the main thing is we now have a system of units that are helpful for us. You can see, for instance, on here, there is a unit vector r hat that points that way. There's a unit vector theta hat in this case that actually is still just in the xy plane. And then in this case, there's actually a phi hat vector that's right there as well. So sometimes those vectors come in handy. So you'll see me write them down, whereas often your book or other textbooks in general will just say n hat where they're saying it's a unit vector because it's got the hat on it, it's a unit vector, and they'll just say n to represent that it's normal or perpendicular to a particular line or a particular vector or a particular surface. Instead of me doing that, I'll have a very specific one we can talk about, r hat or theta hat or phi hat or k hat or something like that. Okay, any questions on those coordinate systems? Again, I'm not going to test you on them. I'm just going to make use of them from time to time, and mostly just for the symbols. Any questions on that? All right, well, let's now start into reminding you first off that if you have two charges, let's say a positive charge and a negative charge, this one has a charge of plus q and this one has a charge of negative q, then you can imagine a vector pointing from the negative charge to the positive charge. Notice its length is exactly the length between the point charge negative and the point charge positive. This vector could be called, for instance, d, where d is the distance between them. Then there exists a electric dipole moment and that vector is in fact given by just the magnitude of the charges, which is q, times the d vector. Well, actually, let me do that with the color red so we can get back to going back to my roots. UD. Ooh, I don't want to do d vector. I want to do d vector, not d hat. Okay, so that's the actual electric dipole moment. By defining that, and notice the weird thing here, the d vector points from the negative charge to the positive. That's important. To positive q. If you get that backwards, then all your answers will be wrong. And it turns out that when you do it this way, you actually get these two really nice results, which I did give you last time. One of which is that the torque on an electric dipole is P cross E, where cross product means the basically the determinant of the matrix, that sort of thing. So in this case, you'd say determinant. You could do it this way. This isn't necessarily the best way. It's not necessarily the worst way. It's just a way that most students, I find, have learned to do it. But you put in the first row of the matrix, you put I hat, J hat, K hat. Then you take the first vector, which is P sub X, P sub Y, P sub J as the second row. And then you put the E sub X, E sub Y, and E sub Z as the third row, and you take that determinant, and that's what the cross product is. So for instance, A cross B, hopefully this is a reminder. If it's not, it's not a big deal. You're going to see it now. Again, this is a determinant, and one of the ways you can do it is do the there's a specific name for it, and I'm drawing a blank, but basically the little multipliers times the remaining matrix. So I have to take each item, each entry in this, and there's 9 of them. For instance, the I is the object in the first row in the first column, so that's ij equals 1, 1. The J is ij equals 1, 2, and the K is ij equals 1, 3. And then, of course, A sub X would be 2, 1. A sub Y would be 2, 2. And A sub Z would be 2, 3. And finally, BX would be 3, 1. BY would be 3, 2. And BZ would be 3, 3. But by doing that, you have a multiplier. It's -1 raised to the I plus J power. So for instance, when I said I hat was 1, 1, that would be -1 to the 2 power. And -1 to the 2 power is just +1. So I don't have to do anything special. But what I do is I write down the I hat. And now I cover up that column and that row. So the first column, which includes I hat, AX, and BX, is completely gone now. And the first row, which includes I hat, J hat, and K hat, are completely gone. All I have left is those 4 little entries in the lower right-hand side, AY, AZ, BY, BZ. And when we have a 2 by 2 matrix like that, the determinant of it is straightforward. You just multiply the top left times the bottom right. So that'd be AY, BZ minus the top right times the bottom left. Okay, that's the first term. Now the next one, I'm going to go with J hat. I didn't have to, but this way turns out to be really convenient. I could have went to AX next. But the main thing is when I go to J, now I'm at IJ equals 1, 2, and -1 to the 1 plus 2 is -1 to the 3 power, which gives you -1. So the way I account for that is I just do my determinant backwards. So I put my J hat. Now I cover up the second column, which is the J, AY, BY, and I cover up the first row, which is I hat, J hat, K hat. So all I'm left with is a 2 by 2 matrix that's AX, AZ, BX, BZ. Normally you go top left times bottom right, but because of that negative sign, I'm going to go top right times bottom left. So I'll say AZ, BX minus AX, BZ. And then finally, I go and expand upon the K hat. In this case, that's 1, 3. That's row 1, column 3. And 1 plus 3 is 4. -1 to the 4 power is +1. So I don't have to do anything weird with the determinant. I just have to cover up the first row, which is the I hat, J hat, K hat, and the third column, which is K hat, is AZ, and BZ. So all I'm left is AX, AY, and BX, BY as a matrix. I do the determinant of that. That is going to be AX, BY minus AY, BX. So that's how you actually take a cross product, and that's something you should be able to do. Okay, it's something that is covered in chapter 21, by the way, so it's definitely on your midterm. Hopefully you've already seen it a little bit in your homeworks, but that's one of the answers. Now the other thing that comes in super handy is the potential energy of an electric dipole in an electric field. In that case, the potential energy U is -P dot E. And remember, A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So if we drew the vectors like this, A and this B, we have them tail to tail, then the angle here is theta. But we could also write it as AX BX plus AY BY plus AZ BZ. Notice this is not a vector. It's called a scalar product. Actually, let me, my A kind of shrunk up there. Or dot product. We use in mathematics and physics and engineering, we use the dot product to find like components, and we use the cross product to find perpendicular components. So that is an ongoing theme with the mathematics of physics and engineering and stuff like that. It comes up all the time. So for instance, we're going to start off in chapter 22 and we're going to use Gauss's law. And in order to do Gauss's law, we're going to have to, for instance, define something called the electric flux. So if you imagine an electric field existing in space, that means literally every point in space, every X, Y, Z that you can imagine in space is going to be assigned a little vector. And that vector, since it's a vector, it's going to have an X component, a Y component, and a Z component, or you can imagine it having a magnitude and a direction. Now, if you wanted to talk about the flux through a particular window, let's say we have a window like this. Okay, then you can imagine this as if it's a window. And if you tried to draw a vector parallel either to the right-hand side or to the top side or bottom side or left side, there's really no good reason to say any one of those are a good representation of the space. But you can reduce it, the ambiguity a lot by saying, I'm going to represent this window's area by a vector that's perpendicular to the window. Then there's just a matter of two possibilities. You could do this guy, or you could do this guy. So that's ambiguous, but it's only ambiguous by two. So that's generally what we do is we say, okay, when we're talking about a flux, we're going to represent a surface area by a little vector A whose magnitude is actually the area of the window and whose direction is perpendicular to the window surface. Okay. Now, perpendicular, like I said, is arbitrary, but it turns out that we only need this in a very non-arbitrary way. In other words, Gauss's law requires us to calculate the flux through a closed surface. That's a surface that has a definite inside and outside. And if you always define the A vector as pointing out of the enclosed surface, then there's no more ambiguity because you'd have to get rid of one of those. Okay, so that comes in handy. If you wanted to actually talk about the flux, though, then maybe your electric field points like this. Okay, and of course, in principle, your electric field could change quite a bit over the space of the window, in which case you'd have to do a little bit more detail. But the main thing is if the electric field was uniform, so a uniform E field with a flat area, then the flux electric would just be E dot A. And it really would depend which one you chose. However, if you have a more general scenario where it's like a window shaped like that, then this little chunk of window dA has a dA vector pointing this way, whereas this little chunk, this little chunk of window might have an A vector that points this way. And this little chunk, again, I keep using the wrong color. This little chunk might have an A vector that points this way. So when you do that, then you come up with the general expression that the electric flux is equal to the integral of E dotted with dA. And that is what we call a surface interval, which unless you're at Princeton, Harvard, Caltech, MIT, or something like that, you're probably not going to get to that section of your calculus course even in the third semester. However, most students that enter, Caltech, MIT, Harvard, Princeton, Yale, Stanford, that sort of stuff, the vast majority of them have already had calculus, and they can just jump right in, assuming everybody knows calculus. So their Calc 3 course can go into differential geometry. It can go into one forms, differential forms, all sorts of cool stuff. And they can do a lot of vector calculus. So they'd actually get into surface integrals and line integrals and stuff like that. We just don't have that time. Okay, so you end up having to learn those branches of mathematics and physics, vector calculus. You have to learn those in your physics classes or your engineering classes. So I've now given you two new things. I've given you that the torque is equal to the P cross E, and the potential energy of a electric dipole is equal to negative P dot E. So those are the two things about the electric dipole. The reason why I mentioned that is you've probably heard of electric dipoles in your chemistry class. For instance, water is what we call a polar molecule. It's like a Mickey Mouse head. And the head of Mickey Mouse, of course, is the oxygen molecule, and his two ears are like the two hydrogen, I should say atom, not molecule, sorry. The two ears are like the two hydrogen atoms, and the oxygen, once it's got those two electrons it steals from the hydrogen, it's acting like a noble gas now because it actually has two more electrons. So it has a lot more affinity for the electrons than do the hydrogens. So Mickey's chin on the Mickey Mouse diagram would have a net sort of negative charge, whereas the spot between Mickey's two ears would have a net positive charge. So you can act as if that's just represented by a positive charge separated by a negative charge of the same magnitude, and you treat Mickey Mouse as if he was, in fact, an arrow pointing from his chin to right between his two ears. When you do that, it turns out there's a lot of cool things you can find out, and you can pretty much ignore a lot of the details of how atoms and molecules interact just by saying, well, they're going to interact like their electric dipoles will. And in fact, that's the basis of the MRI device. For instance, when you have a MRI, which, by the way, is supposed to be called NMRI, which means nuclear magnetic resonance, because what happens is the atoms in, let's say, for instance, the water molecules that are inside of your body, when the MRI device comes on, it can switch from one polarity magnetic field to another. That actually causes the electric dipole of the water molecule to flip from pointing one direction to another. The energy difference between those two directions is a very specific known quantity. And therefore, when we get a photon that hits the receiver inside the MRI device, it says, oh, I recognize that energy. That's the transition of water molecule from, one polarity to another. And therefore, you can identify where water is, stuff like that. But you can also find other things. For instance, when we first started to learn about Alzheimer's, it was discovered that the brain of Alzheimer patients often had aluminum spikes in it. So you'd actually have a graph. In addition to the cool picture of the MRI, you'd have a graph that has all these little spikes on it. And those spikes correspond to very specific wavelengths or energies. And those very specific wavelengths or energies tells us what atoms, molecules, compounds, elements, or whatever are present. And for instance, if you had a lot of aluminum in your brain, then you'd have a spike lined up with the energy level or the wavelength level for aluminum. And that was what was thought initially when we first started doing these brain scans on people with Alzheimer's, is they had aluminum. And there was a brief period on a matter of a couple of years where people were advised that we didn't really know what the purpose is, but there may be some reason to be aware or a little bit worried or concerned about using aluminum cookware, aluminum cans, stuff like that. We've since determined that that's not the case. It seems basically whatever problem is causing the Alzheimer's is probably the same thing that's causing the aluminum spike. So the aluminum spike wasn't causal to the Alzheimer's. So anyways, just some sidebars on science and how that stuff works in other fields. So that's a relevant thing. Now you know how to deal with that. You should be able to create a vector. Remember, I told you one way you can always create a vector from one point to another is you take the x, y, and z of the point where the head should be, which is the end, and you do the x of that minus the x where the tail should be, and that'll be the x component of the vector. You take the y where the head is minus the y where the tail is, that should be the y component of the vector, and then do the same thing for the z, and you'll get the z component of the vector. That will give you a vector that literally goes from x1, y1, z1 to x1 or x2, y2, z2. Now, if you wanted to use that to multiply by a vector whose magnitude you know, or multiplied by a magnitude that you know, then that would screw things up because the magnitude of that vector is multiplying by the magnitude of the number you had. So you then try to normalize it, or excuse me, try to unitize it. So you could actually force the vector to become a unit vector by dividing each component by its magnitude. So if the vector, for instance, was 7.3 units long, you'd divide the x component by 7.3. If it was in meters, you divide it by 7.3 meters. You divide the y component by 7.3 meters, and you divide the z component by 7.3 meters. Then you have a unit vector. And since the top and the bottom are both in units of meters, you would purely have a unit vector, meaning its length is 1 unit with no meters, no centimeters, no newtons in it. Anybody have any questions on that? So these cross products, dot products, those are things you should be able to do. I know we've done dot products last semester. We even in 241, for those of you who had me for 241, those of you who didn't have me, you probably covered them to some extent when we did torque for cross products, and you did dot products we use for calculating work. So that should be something you should be able to do, and it is something that's already in chapter 21. So you definitely want to make sure you have that ready for the midterm. Again, the midterm, by the way, I'm calling it the midterm because I can count those face-to-face tests as having more value than the online tests. But they're really all going to have the same value as tests in general. So you don't worry about it being something that could make the end of your, physics career or something like that. It's not that kind of midterm. It just means that the sum of all the face-to-face tests is going to be worth about 20%. And then the final exam is going to be worth about 25%. So all those tests combined plus the final exam gives you a net of 45% of the course. So only in that sense is it really that dangerous or a midterm. Anybody have any questions on any of this stuff? All right, so let me get started by doing something like calculating the flux. So let's say we have a window. Let's say, let's say this window, there's my x-axis, there's my y-axis, and there's my z-axis. And let's say this window actually has its bottom running right along the x-axis like that. But then this part runs like that. That's a little confusing. Actually, I don't like that at all. That makes it really hard to draw. I should have done a better angle. Let's do an angle like this. Okay. So this side right here, let's say that angle is 15.0 degrees. And let's say this length is 3.00 meters. And let's say this length is 2.00 meters. And let's say our electric field E is equal to 150.0 newtons per Coulomb, and it points purely in the j hat direction. What I want to know is what is the electric flux? Okay, so this is the electric field right there. I just stated it, and you can see it doesn't have any t dependence. It doesn't have any x dependence or any y dependence or any z dependence. It is just a vector field that basically for every point x, y, z in all of space, it's going to point to the right and have a magnitude of 150 newtons per Coulomb. Okay. Now, the way we calculate the electric field, since that, or excuse me, to calculate the electric flux, since that electric field is uniform and constant, and since the area is uniform and constant, we just need to form a vector perpendicular to it and to represent the a vector. But really, it doesn't even matter that much. It just matters that we have to take a dot product of that a vector with the e vector, because the magnetic flux solution is phi e is equal to e dot a. Okay, so what I can do is I can imagine a line parallel to the z-axis and a line parallel to the other side like that. And now I'm going to draw a vector that's perpendicular to it. That's my a vector. And the magnitude of that a vector is going to be 3 meters times 2 meters, which would be 6.00 square meters. And it's going to point in the n hat direction. So there's me using that n hat stuff I was telling you about. And this indicates that it's perpendicular to the plane of the mirror. Okay. Now, what we know is if we look, take this three-dimensional aspect out of it, and if we look right along the x-axis, so here's the arrow that represents the x-axis coming straight out instead of at some angle, then the y-axis goes straight like this. And in fact, that arrowhead would look like this. Okay. And then the z-axis would go, would go straight up like that. And of course, that too would look like that. If we have this scenario, then what we would see is this, I should do blue. This window makes a 15.0 degree tilt like that. And this a vector is 6.00 meters squared. In fact, it has a very specific direction. For instance, you can say by symmetry, we know that this is 15 degrees. And by symmetry, we know that this is 15.0 degrees. So we can say the magnitude of A is 6 meters, but in fact, A is going to be the magnitude is going to be 6.00 meters squared. Now I want the x component, and I think you can see that that would be the y, or that would be the z component, and this would be the y component. And in fact, it doesn't have an x component at all. So this would be a sub y, and this would be a sub z. So we can say that the x or the y component would be negative 6.0 meters squared times the sine of 15.0 degrees. And then since it's parallel to the y-axis, I'm going to put a j hat here. And then the Z component is going to be positive, but that'd be 6.00 meters squared as well, times the cosine of 15.0 degrees. I'm gonna have to write that smaller to fit that in, so let me redo that. So this is going to be 6.00 meters squared times the cosine of 15.0 degrees, and all that times k hat. Okay. So computing this, I'm going to say 6 times sine 15 is giving me negative 1.552. Actually 1.553, carrying one extra sig fig, meters squared j hat plus 6 times cosine 15 gives me 5.796 square meters k hat. So there's my actual A vector. I don't have to do all this, okay, guys? I'm just showing you this is brute force. If anything's really, really ugly and hard to do, you might have to go back and actually figure out what the A vector is that is actually perpendicular to the surface. In this case, it's immediately obvious to me that the angle between the E vector and the A vector would in fact be 15 plus 90. So really all I have to do is take the 150 newtons per Coulomb times the 6 square meters times the cosine of 90 plus 15, which would be 105. And that should give it to me. In fact, let's try that. 150 times 6 times cosine of 105. That gives me 232.9, so you might as well call it 233 Newton square meters, or excuse me, Newton meters. Okay, so that's what it should work out to be. Now I'm just doing brute force here to show you how you could go about doing it. The electric field vector, of course, is purely along the y-axis. So now I can take and calculate that the electric flux is equal to E dot A. Well, the way we do a dot product is we multiply like components and add them. So E has no X component, so that'd be 0 newtons per Coulomb times 0 square meters. There's no X component on the A either. So that's why I had that, plus now I have E does have a Y component. That Y component is 150.0 newtons per Coulomb times the Y component of the A vector, and that is negative 1.553 meters squared, plus now I've got to do the Z components. Well, A has a Z component, but E does not. So it's 0 newtons per Coulomb times 5.796 square meters. Obviously, this whole part is 0. This whole part is 0. And I get 150 times negative 1.553. That gives me, in fact, negative 232.95 Newton meter squared per Coulomb. Okay. I said before that I could have just taken 150.0 newtons per coulomb times 6.00 meters squared times the cosine of 105 degrees, and done it that way because I knew how this was behaving. And when I did that math, I in fact got negative 232.937. And again, that's Newton meters squared per coulomb. So you see, I really did get the same value, whether I did it the brute force horrible way where I had to compute all the components of vectors and stuff like that, or if I just did magnitude times the angle between them when they're tail to tail. Notice the negative comes out because the actual A vector is pointing up and to the left, whereas the E vector is pointing to the right. So the components that are in fact parallel to each other of A and E are actually in fact anti-parallel because the E one goes to the right and the A one goes to the left. That's why you get a negative. So that's why the number came out negative. Anybody have any questions on how that one was done?
Yeah, I do have a question. Sorry,
No problem.
So I have a question about when you try to find the direction for the A vector A,
Mm-hmm.
and how do we know that it's like pointing out or pointing the other way?
We don't at all. I just chose it. Remember, I told you if we had a closed surface, there'd be no ambiguity as to whether the A would point up like this one does or down and to the right like the other one would. I just happened to choose up and to the left. That gave me a negative value. If I'd chosen down and to the right, it would give me a positive.
Okay, so the direction here doesn't really matter.
In this part, no. But when we do Gauss's law, that's going to have a flux of a closed surface, and it will matter there. I'll show you that's actually the very next example I'm getting ready to do. So that'll make some sense to you then.
Okay, thank you.
No problem. Anybody else have any questions? Okay, so that's what this electric flux is. And people like Michael Faraday and Alejandro Volta and Gauss and all these people notice that this flux, this sort of measure of the electric field times the area that it goes through perpendicularly, that was something that was relevant to the physics and the physical systems that they were studying. So they knew it was something important. And ultimately, like I said, Michael Faraday had made these wonderful notes, but with no math because he really didn't have much more than a sixth grade education. But he was a brilliant scientist, and he had described things so perfectly and so imaginatively that Maxwell could just read his notebook and translate it into mathematics and got what we now call Maxwell's equations. I would say I don't want to take anything from Maxwell here. Maxwell did, in fact, find an error that probably would have taken decades more before Faraday would have found it. But he discovered a illogical inconsistency with Maxwell's equations, fixed that, and then wrote the equations. And if it wouldn't have been for that, we wouldn't know about electromagnetic radiation. We wouldn't know that light is made up of electric fields oscillating in one plane, magnetic fields oscillating in a perpendicular plane, and then the light traveling itself in a direction perpendicular to both of those planes. So all of that was a really big feat for Maxwell to do as well, but Faraday was really quite brilliant with his experimental apparatus and things he came up with. So what we ultimately figure out for Gauss's law is that we need this electric flux. So now I'm going to say Gauss's law. So it's GAUSS' law. And actually, I'm not going to define it yet. I'm going to do a calculation of it, of one side of it, and see what it works out to be. And lo and behold, that particular choice gives us exactly the right answer. So again, I'm going to draw a coordinate system. Okay, this is my x-axis. this is my y-axis, and this is my z-axis. And for Gauss's law, I'm going to say the flux, the electric flux through a closed surface is closed integral E dot dA. So this is not a mathematical symbol that you will see in your physics textbook usually. I mean, in your math textbook usually. You only see it like in physics or engineering. When they put that circle on there, that's sort of a little reminder for you to say, hey, I can't use this expression unless I'm dealing with a closed surface. In other words, a surface where you can definitively say this point is inside of it and this point is outside of it. For example, it couldn't be a toilet paper roll or a paper towel roll, because a paper towel roll, you might argue this little dot dead center in the paper towel roll is inside of it. So let's look at a paper towel roll. So you might argue that this little dot inside of there is inside, and everybody would agree with you. We all would agree with you. But here's the problem. I don't have to cross any surface to go from here to right out here. Now everybody agrees that that same dot is now outside of it. So if you wanted a paper towel roll to be a closed surface, you'd have to put end caps on it. Does that make sense? So that little circle on the integral is the kind of thing that we put there specifically so you'll remember it. So now what I'm going to do is I'm going to imagine a little point charge right here at the origin, a small in size charge Q is centered at the origin. Okay. Now, since it's centered at the origin, can someone tell me which direction, say, the electric field would point due to that charge right there on the z-axis? So it's a positive charge. So remember, the electric field points in the direction in which a positive test charge would be compelled to move if you put it there at that red dot. So which way would a positive charge be compelled to move if it was at that red dot? Bohan, do you know this one?
Sorry, no.
Okay. Anybody else think they know it? It's okay if you get it wrong. I mean, it's just try to give it a guess. You've got a positive charge sitting right at the origin. And in fact, there's going to be a point directly above it, that little red dot, where you're going to imagine putting a positive charge. So that positive charge is going to want to, what? Is it going to move towards the blue one or away from it?
Away.
It's definitely going to move away. And were you going to say something else there, Drew or Bohan? I think it was Drew.
No, I wasn't planning on it.
Okay. So you do agree that it would move away. Would you say it would move away with the x component of velocity, with a y component of velocity, or
Would it
with
be
a
along the z-axis?
There you go. That's exactly right. It's going to move exactly along the z-axis. Okay. What about if I had a point right here? Which way would it move? Anybody?
Along the y-axis?
Along the y-axis. How about right here?
Along the x-axis.
Yep. That, my friend, is what we described in the spherical coordinates as the radial direction. See that R vector always points away from the origin. Would you agree that the electric field here always points away from the origin?
Yeah.
So that's what I'm getting at. So you have, in some sense, a feel for a spherical distribution of charge that you know because Coulomb's law says the electric field for a point charge is Q over 4 pi epsilon naught. And let me get rid of the vector symbol because we know the magnitude is E over 4 pi epsilon naught, R squared. Whoa. It keeps doing that to me. Over R squared, where R is the distance between the center of mass of the charge Q and the point P, right? Or the red dot. So we know that magnitude. So would that suggest, or let's do it this way, on what kind of surface would you suggest the electric field is a constant in magnitude? Can anybody see that? Oh, I see y'all were answering. Good job. I just saw your chat. Sorry about that, everybody. Can y'all imagine a shape that you could maybe put around this charge, bigger than the charge, obviously, but around this charge such that the electric field would be a constant everywhere on it?
Circle, like a sphere.
Exactly. A sphere is exactly it. And that's what we're going to do here. I'm going to change colors real quick. I'm going to now draw what we call a Gaussian surface. And it's going to be a concentric sphere, meaning it has the same center as the spherical charge, like that. That's going to be called my Gaussian surface. Now, the deal with Gauss's law is you can use any closed surface you want. And then you're going to calculate the flux through that surface, and we're going to try to figure out what you get. But by me choosing a Gaussian surface that is centered on the origin and has a radius, let's say big R, then I know exactly what the magnitude of the electric field is going to be everywhere on that surface. And I know also what the direction is going to be everywhere on that surface. So let's take, for instance, that little spot right there. I can imagine this being a itty bitty rectangle. And in fact, I'm going to ultimately break it down till it's infinitesimally small. And with it being infinitesimally small, then it looks flat. So you can integrate over it really easily because the electric field is going to be about the same. But the main thing is right there, I'm going to have a dA vector that is in fact equal to the magnitude of dA and points, again, using our new coordinate systems that we just talked about, it's going to point radially outward, right? So I'm going to say its direction is in the R hat direction. I'm going to hypothesize or claim that E, the electric field, only depends on R. So it's going to be E of R, where R is the spherical coordinate R, but it's going to point radially outward. Okay, that's the conclusion we reached when we found that the red dot on the z-axis was going to compel a positive charge to move in the positive z direction. Same thing for an x-axis red dot, and same thing for a y-axis red dot. All of those things are pointing radially outward. Does that make sense to everyone now?
Yeah.
Okay, so now what I'm going to do is calculate this quantity. I'm going to calculate the electric flux, which is equal to integral over the closed surface of E dot dA. Well, all that means is I'm going to take an integral of E of R hat dotted with dA, and there's actually, if you wanted to study spherical coordinates, you'd find there's a very specific dA that works really easily here. It requires a double integral, but we don't need that. We don't need those details. We just need to know that there's a magnitude we're going to call dA, but that it points in the direction of R hat. Okay, and I want to say on sphere of radius R. This is a surface integral. So when I say on the sphere of radius R, that means, hey, I know this is a surface integral and I'm going to compute it on the surface. So what's going to happen is, because it's on the surface of that green sphere, I'm going to be integrating E, not of little r, but E of big R hat, dotted with dA R hat. Now I'm going to use the linearity of the dot product. So I'll put right here, dot product is linear. And what that means is, if you put in some constant times a vector plus some other constant times another vector, and you take a dot product with that, then you can pull the first constant out in front and do A dot B for the first vector, and then you can pull the second constant out front and do A dot C for the for the second vector. So that's what I mean by linear. So I can now change this integral to the integral of E of R dA times R hat dot R hat. Now, I just gave y'all a nice description of how you can calculate a dot product. So can anybody tell me what R hat dot R hat is? You can look right there. A dot B equals AB cosine theta. Everybody see that right here? So what is R hat dot R hat going to be? Notice the hat means it's a unit vector, so its magnitude is 1 unit, not 1 meter, not 1 Newton, not 1 Coulomb, but 1 unit. And they're both unit vectors, so it's 1 times 1, that's A times B. And what's the angle between two identical vectors?
0.
So we're going to take the cosine of 0. And when you do 1 times the cosine of 0, what do you get?
1.
1. So R dot R is 1. Not only that, because we're integrating on the surface, E of R is a constant. So I can just say E of R times the integral of dA over a sphere of radius R. So the integral of the surface area element over the entire surface area is the surface area of a sphere, right? And can anybody tell me what the surface area of a sphere is? It's okay if you don't, but
Isn't it like 4 pi r squared or 4/3 pi r squared, something like that?
exactly. The volume is 4/3 pi r cubed, but
Oh,
the
okay.
area is 4 pi r squared. So you're exactly right. So by the way, we knew from Coulomb's law, since we're on a sphere of radius big R, the electric field strength was Q over 4 pi epsilon naught big R squared. So I just substituted that in for E of R. Let me do that by showing this. Okay, and the integral of dA is just going to be 4 pi r squared. So you can see right now that in doing this, the 4 pi cancels out with the 4 pi and the r squared cancels out with the r squared. So ultimately, I just get that the electric flux is the charge over epsilon naught. Well, guess what? We did this for a very specific case where we very specifically knew what the result was and what the electric field was, and we got a very specific answer. Well, it turns out that answer is exactly the right answer for the most general case. So I'm going to say Gauss's law says the closed integral of E dot dA is equal to Q enclosed by that Gaussian surface divided by epsilon naught, and that is Gauss's law. Okay, so you can sort of think of this as like a derivation of Gauss's law, and there's a process you can go through to derive it from the differential equation that we know of as Gauss's law. But this is just almost like a heuristic argument for what Gauss's law is. What we found is that any closed surface will have an electric flux equal to the charge enclosed divided by epsilon naught. And that's it. We're done for the day. Next time you guys during lab will have a quiz on, a midterm exam, which is really no more than any other face-to-face test, but it'll be on chapters 17, 18, 19, 20, and 21. This stuff right here that I did with Gauss's law, that's actually chapter 22, so that's not on there. However, neither is this stuff. But this stuff is up to the little black line. Okay, so the little black line is where we started into chapter 22. So that's not going to be on the test, but all this other stuff will be. If you need to speak with me before Wednesday at lab time, you can text me. Do text me. Don't send me an email. It'll take too long for me to reply. So text me, let me know. We'll see if we can set up a Zoom meeting. If I do decide to set up a Zoom meeting to meet with someone, I'll let everybody know so everybody can show up that wants to. But the main thing is I just want to give y'all another chance in case you have any last minute questions. You can do that tomorrow during the day or whatever. I also have office hour tomorrow morning from 9 a.m. to 10 a.m. I could even be there earlier if y'all need me. And then I have another office hour during lab. My lab starts at 12:45. So usually by 1:30, I'm usually free to answer questions. So y'all can also come by JC 26 and get questions answered then as well. Okay, have a good one, everybody. I hope y'all do really well on the on the midterm, and I hope you have a good day and a good night. Stay safe.
Have a good night.
You too. Thank you. I'm stopping the share.
Professor Younger.
Yes.
Okay. Can I ask you one question? It's on your notes, the last page. If you turn your notes on it, it's just the last page that so when we talk about electrical field, I know the formula, the equation, it's sorry. So whatever they had like on the bottom, it was like 4 pi r square.
Right.
But yeah, absolutely. When I do the one question, they were asking about it was differently. It was like non-conductive object, and they said that inside, try to calculate the electrical field, but the R was less than the radians R.
Right.
So it's in the middle, and then the formula changed to 4 pi epsilon R third power. So everything's the same, but instead in the square R is like 3 power. I just don't know where that comes from.
So was this in chapter 22 or chapter 21?
I think it's a 22.
Yeah, that makes sense. So it turns out that if you, and you'll see some of the problems I solved on my YouTube channel does this, but if you're actually trying to calculate the electric field inside of an object,
Mhm.
then you have to compute how much charge is in there. And if it's a conductor, then the conductor, in fact, will behave such that all the charge will run away from each other until it's all evenly distributed on the outside surface. If it's a
Mhm.
sphere, it'll be all evenly distributed. So there'll be no charge inside. In fact, you'll get zero electric field inside.
Yeah, I saw that question too. So they said like in the middle, if it's a conductor, should be zero charge.
Right. And that's just because the conductor, the definition of a conductor is that its charges are free to move.
Mhm.
And charges that are all alike, which are basically electrons, don't like being near each other. So they maximize their distance apart, which means they go out to the outside surface.
Okay, so if there's a question asking like electrical field in the like inside the conductor, that should be like zero because no charge.
Yes, there
Okay.
will be times where you can have an electric field inside, but like if you had a sphere with a spherical hole,
Right.
and you put a charge inside that spherical hole, that spherical hole or that charge in the spherical hole would cause the inside surface of the spherical hole to be charged with the opposite charge of the charge that's in it. So if it was like
Okay.
3Q,
Yeah.
it would be negative 3Q.
Right.
So
So
little stuff like that. But generally, yeah, the conductor inside the actual metal of the
Mhm.
conductor, the electric field will mostly be zero unless you have a voltage across it, like a battery or something. And then an electric field is really what makes the current go.
okay, and for the non-conductive, use the object you said that's gonna be R3 power.
Well, it could. So for instance, I could tell you that the charge would be if you said it was uniformly distributed, that means if you took out any 1 millimeter by 1 millimeter by 1 millimeter chunk, it would have exactly the same charge as any 1 millimeter by 1 millimeter by 1 millimeter chunk that you came from somewhere else. But you could also sometimes they'll say, all right, the charge is directly proportional to R. So charge density, and then when you integrate that, you find that you could actually get electric field that goes like R cubed or R squared or R to the 1 is the one we normally do. But yeah, you can get all those different powers.
Yeah, I just saw that question that actually the formulas are like cube. That was like a little bit weird. Everything's the same, just inside in the R squared.
Yeah, they're probably using rho is equal to some constant times R squared.
Oh yeah, they use that because they said the whatever the charge density, the rho,
Right, rho.
it's on the continuously something on the project. Like
Yep, that's it. Because when you go to integrate it, you integrate rho over dv, and the dv is going to be like 4 pi r squared dr.
Okay.
If you had k times r squared, you're going to end up integrating r cubed, and that give you r to the 4th. Or
Okay, that makes a lot of
r
sense.
give you r to the 3rd.
Okay, I see. That makes a lot of sense. Yes.
Yep, so that's it. Don't worry, you're going too far ahead, so that's not going to bite you at all in the test. And good luck.
I did a couple of times the practice test. I feel like I'm just struggling on those like language. It's a lot of readings there, like different words. Sometimes like the consonant, I kind of know, but I just need to figure out like what they really try to ask. It's just I still need to work on my language a lot.
Yeah, you're doing way better than my Mandarin, so I'm going to give a 100 on that.
Thank you so much, Professor Younger.
No problem. Hey, if you run into a problem where you don't know what a word means or something like that, ask Kevin, Mr. Mitchell, when you're there. He'll help you. He knows he should be able to. Okay.
Okay, I try. I try.
Right.
Hopefully.
See you, Rohan. Have a good one.
Thank you, Mr. Younger. Have a nice evening.
Nice evening to you. Bye bye.
Bye bye.